students joined us yet?
No, I just see one teacher or staff.
Share their video and they can't.
No, the students cannot. I have to, like you were the attendee, so I have to make them a panelist in order for them to share, which we will not because that's the point of a webinar. But the students can, there is a question and answer tab, just like there is chat. So when the presentation is done, students will be able to write their questions in the Q&A tab.
So can they chat during the presentation? They have to wait till the end.
No, they can.
The chat function is the Q&A there.
Yeah, I see the students coming in now.
So what's the difference between chat and Q&A?
Sorry, what?
What's the difference between Q&A and chat? I guess I've never
Nothing really. Chat is just like a messenger. So for the Q&A, if you click, we have the option of how many questions are there, how many have been answered, how many do you want to dismiss because they are students. They might ask some questions which you really don't want to put it in front of anyone. So the Q&A tab just have all those features, and chat is just like a normal messenger. But the students can do both. They can put their questions in the chat also or in Q&A, whatever they are comfortable with.
Welcome, Nick. Are you a student or a teacher? Probably have to use the chat function.
Now, Nick is listed here as an invitee, so I'm assuming either a staff member or a teacher. That's why I've promoted him.
There were 7 people signed up. So I guess we can give it a couple minutes. Nick, are you by yourself or is there more folks with you there?
I see 2 or 3 more teachers or staff signed up. Let's give them a few more minutes to join. Okay, let's give them another 2 minutes. It will be 5 minutes over the session and then we can start.
Nick, can you hear me all right? Can you type something to the chat so we know you got good audio?
If there's a teacher or a staff member in the attendees, please put it in chat and I can promote you.
We got a pretty good list. I got Angie and Faith and Hannah, Iris, Jada, Lynn,
Yeah, they are all students.
Haley, Victor.
Okay. Thanks for clearing that out, Nick. Nick, you should be able to turn on your video. Yeah. Okay, it's 5:05 Central, so let's start the presentation. Jason, all yours.
All right, thank you very much. Well, good afternoon, everybody, and welcome. My name is Jason Kelly. I'm a civil engineer with DOWL. Today, I'm going to talk about a bridge project that I'm working on, but really I wanted this to be kind of an informal discussion, give you all a chance to ask questions, give answers. I do have some kind of general bridge design information up front. We can talk, but feel free, if you've got any questions, please add them in the chat or in the Q&A, and we can just have a good discussion as we're going along. So the project I'm going to talk about today is the Clackamas Regional Mobility Project over in Clackamas, Oregon, near the Clackamas Town Center Mall. So raise your hands if you love bridges. I definitely enjoy bridges. Loved them since I was a kid. I think fascinated with just, being able to get from point A to point B without getting your feet wet, or maybe get falling into quicksand. So this is a picture of a bridge that my company designed. It's the Minto Island Bridge down in the city of Salem. It's a pedestrian bridge. It's an arch bridge that was designed to get access out to Minto Island. Yeah, definitely, Nick, encourage folks to ask questions, and I'm here at your disposal today. And if there's anything specifically you want to learn about bridges or have a burning question, I'll definitely answer it for you. So it's good to start off with a quote. So here's a good one I like. Bicycling is a big part of the future. It has to be. There's something wrong with a society that drives a car to work out in a gym. All of you are familiar with Bill Nye, the science guy, but that was a quote attributed to him. So one thing that I kind of found interesting about Bill Nye, reading his bio, so Bill actually has a Bachelor of Science in Mechanical Engineering from Cornell. He actually got his start as an engineer, less as a general scientist, but as an engineer. He actually started his career working up in Washington State for Boeing. He actually worked on the development of the Boeing 747 and actually invented a part for the Boeing, the hydraulic resonance suppressor tube. I couldn't tell you what that is, not being a mechanical engineer, but it definitely sounds cool. So, a little bit more about me. So I graduated from Canby High School many years ago, so I'm a local Oregonian. After I got done at Canby, I went down to Oregon State University in Corvallis, got degrees in civil engineering and also got a degree in forest engineering. Wasn't quite sure what I wanted to do. Really loved forestry and working in the woods though, but I also wanted to kind of have a fallback, and there's a lot of overlap between those two degrees. But ended up using my civil engineering degree. Always loved working out in the field and getting dirty and using my hands. So I've always worked out in the field. In my career, started out doing surveying and then moved on to construction engineering and ultimately construction management. So that's kind of my specialty. And then I'm a lifelong learner. Of late, I went back to school, got a master's from George Fox University. Any questions about me or what I do or anything? Don't be shy. So I guess, next I just wanted to talk a little bit about, civil engineering in general. Civil engineering is not really just one job or one career. It's actually a huge field. And if you're interested in engineering, there's really a job for anyone and everybody. And I don't work on projects by myself or with one or two people. Every project that we deliver is a huge team of folks, engineers and scientists and professionals, and we all work on a big team to deliver projects. So almost every project that I work on has one of these types of jobs. We have planners and surveyors, a lot of different types of environmental engineers and biologists, cultural resources folks look at the historical natures of our projects and archaeological issues. And then we have the engineering designers, like the hydraulics designers that are experts in water and fluids, our geotechnical engineers that are experts in soils that help us with our foundations for our bridges, our traffic and transportation engineers. They really provide how the roads are going to flow and how they get up and over our bridges. Then we have the bridge structural engineers, which you all may be interested in. Construction engineers like myself that make sure it gets built properly, and then a whole host of other engineers. So lots of different folks. They're different educations and backgrounds, but it's a big team effort. And, it's a great industry to be a part of. Just a few general background on bridge types and what they're about, how they're made up. There's traditionally 6 main types of bridges that we work with. There's beam bridges, which are the most simplest and basic bridges. There's truss bridges, which I'm sure you all see out and about, kind of an older style bridge, but definitely have their place. Big cantilever bridges, like the Astoria Megler Bridge out on the coast. There's arch bridges, which historically are very common, less common nowadays, but we still do arch bridges, a lot of concrete arch bridges. We have a lot on the Oregon coast. Suspension bridges like the St. John's Bridge in North Portland, which is really a world-class bridge. If you haven't been out to the St. John's Bridge, I definitely encourage it. That's a world-class suspension bridge. And then cable stayed, which are becoming more and more popular, like the Tilcomb Crossing Bridge in downtown Portland, or there's a cable stay bridge over at I-5 in Eugene that I helped work on. Definitely these days. But each type of bridge that I showed before, they really have many subsets. There's not only one type of beam or truss bridge or arch bridge. There's probably 6 or 10 or 20 different subtypes under that. So I was going to focus a little bit on beam bridges today because that's the bridge that we're going to talk about. But these are some of the beam bridges that I've worked on over the years. We have pre-stressed concrete boxes that are hollow in the middle, like the upper left there. Those are good for smaller bridges. We have trapezoidal steel box beams, like the one in the upper middle there. That's the Fremont Bridge. I've been working on the Fremont Bridge in downtown Portland the last couple of years. We have just kind of run-of-the-mill concrete pre-stressed girder bridges like the one in the upper right. We also have steel beams like the lower left. That's the Tolbert Railroad overcrossing in Clackamas that we built a few years ago. And then also timber bridges. Timber is still pretty common here in the Northwest for pedestrian bridges and some of the older bridges like covered bridges. So we still use timber girder bridges too. That's Harris covered bridge down in Benton County that I helped work on several years ago. So the projects I'm going to kind of talk about today, just kind of talk a little bit about the design, and then maybe show you some videos of construction that's going on right now and some photos. And then talk a little bit about post-tensioning. Yeah, so that's kind of the plan. So we'll talk about the overview, the existing bridge, the plan modifications, and why we're doing that, and then post-tensioning. So this is the bridge we're going to talk about. So this is the Sunnyside Road overcrossing over I-205. So if you live in the Portland area and drive on 205 to go to the airport, or maybe you go over to Clackamas Town Center, you more than likely probably driven over this bridge or under this bridge many times. And it's a beam bridge, but it's a post-tension cast-in-place concrete box, is what it's called. And it's continuous over two spans. So the superstructure concrete boxes, it's one long continuous thing for both spans over both north and southbound directions of the freeway. And this is kind of the project in general. So there's Clackamas Town Center, there's the 205, there's the bridge in red that we're working on. And then the yellow is the total project. And I put the project website in the chat if you want to click on that link and kind of cruise around the website. You can learn more about the project in general. But it's kind of a regional mobility project. It's trying to improve a lot of efficiencies in this area. Some of the things they're doing, they're putting in new crosswalks for pedestrians and new sidewalks and widening existing sidewalks. They're upgrading landscaping, building stormwater swales that help to treat the water so the quality is a little bit better before it goes into the local streams and rivers. And also it treats the quality so that when it rains and all the water off Clackamas Town Center and the roads don't just rush into the rivers and create these flash floods, it also kind of regulates the flow of water before it hits our natural streams. They're also doing bike lanes and some turn lanes, upgrading some traffic signals and striping, and then widening the bridge. So lots of pieces to the project to make bikes and peds and vehicles all just kind of move through the area. So here's the bridge. So Sunnyside Road overcrossing. So it was built in 1966, the same time that they built I-205. So before the freeway was there, before the mall was there, pretty just rural Clackamas County. And it's getting towards the end of its life. Most of the time nowadays, we're designing bridges to last 75 to 100 years. So this one's, 50 some years old. So it's about 2/3 of the way through its life. So it's still lots of life left. It's two-span continuous, like I said, and then it's the box beam. In the upper right-hand corner, you can see some of the original plans. The top is kind of an elevation view from the side, and then the bottom view is the typical section at the median there between the north and south bounds, and you can kind of see the boxes, these individual boxes with these cells and these webs. So this bridge is actually hollow inside. It's not just one big solid chunk of concrete. So in widening the bridge, they're doing it for three main reasons. One is seismic resiliency. A lot of the bridges that were built prior to the 1990s, they weren't designed for earthquakes at all. So right now, these bridges have 20, 30, 50 years left of life, but if an earthquake strikes, they could potentially fail. So we want to upgrade these bridges to make sure that they're resilient. They'll be in service after an earthquake. We want to widen the bridge. to create wider sidewalks for bikes and peds, more lanes for cars. And then we also want to do for safety. You know, they're going to take the bikes off the road and put them up on wider sidewalks. It's going to get new railing. And also widening plays into safety as well. If traffic is constantly backed up, that causes a lot of rear end accidents. So widening will also make it safe by hopefully keeping cars moving, not causing a lot of rear end collisions. So I wanted to dive into a little bit deeper on why and how for the modifications. So there are three main types of seismic vulnerabilities we look at bridges. There's liquefaction, bearing failure, and foundation failure. Now, liquefaction is basically in an earthquake, the ground shakes and it liquefies and it becomes like quicksand, you know, where you have these fine soils like sand and they have just enough water in them that when they're shaking, they liquefy. And then, you know, bridge foundations fail or buildings tip over like the photo. So that's kind of what we're trying to prevent when we look at liquefaction. You know, is the bridge sitting on those liquefiable soils that cause the bridge to sink? The next one is bearing failure. If you look at that photo in the lower left there, basically the bridge shakes, the foundation is fine, but the girders aren't really secure on the foundation. The foundation is too small, or they're just not strapped down, and they just fall off. You know, and it can be fixed. You can pick the bridge beams back up and put them on the foundation, but it takes time and money. So that's something to look at too, is bearing failure. Will the bridge just fall off its bearings? And the last one is foundation failure. Based on the soils and the bridge type and the weight of the bridge, is the foundation too weak? Is the concrete too weak? Does it not have enough rebar in the columns? Will it just crumble and crack and explode? So that's kind of what bridge engineers are looking at when they're looking at these old bridges. It's like, will the ground liquefy? Let's talk to the geotech engineer and see. What do the bearings look like? Is the bridge beams going to fall off in some shaking? And then thirdly, what's the foundation? Is it strong enough? Is it going to crumble? You know, so that's what they'll look. So when we looked at this bridge, the geotech came out and looked at the soils around there, and they weren't really concerned about liquefaction. There's good bedrock, basalt, lava rock, pretty shallow under it, so they weren't really worried about liquefaction. They looked at bearing failure, and based that the bridge is two-span continuous, and it's cast into that center pier, and the end piers have plenty of room for the beam to sit. They weren't really worried about bearing failure at all. But then they looked at the foundations, and they looked at this pier out in the middle, out in the median between the two. And they said, you know what? This footing is kind of small. It doesn't have a lot of rebar. The pier is small. It doesn't have a lot of rebar. And they modeled it in the computer, and the computer said that pier is going to crumble. There's an earthquake. So what they did was they went in and they did a number of things to this center pier. One, we went in and we increased the size of the footings down there. We made it bigger. And then we drilled some rock anchors down and tied it into that lava rock under there. So that made the footing all nice and stout and strong. It's not going to fail. And then we went into this pier wall, and we went in there and we drilled all these holes. You can't really see them, but we drilled all these holes and we put more rebar inside this thing. And then lastly, we came in and we wrapped it in this carbon fiber reinforced polymer. That's what you see in this photo here, these black strips that we glued on this carbon fiber. And between all that stuff, that'll keep that pier, that concrete, from exploding and crushing and just buckling and falling apart between adding the carbon fiber and the rebar and everything. So this bridge didn't take a whole lot to make it more resilient to earthquakes. We just needed to fix that one deficiency. So that's one goal. So now this bridge is seismically resilient. It's not going to fall down in an earthquake. And then the other modifications we're doing for widening and safety. So in the lower left, you can see the plans. So that's some of the new plans. On the right side is the old piece. This is the old bridge. And then this is the new bridge. And you can see we added 2 more lanes. We widened out this sidewalk and we're making a new wide sidewalk, 12 feet wide on either side. I think the existing one's probably 5 feet. So the existing one's really not big enough for bikes and peds. It's pretty tight. So this will have nice big sidewalks on both sides that bikes and peds can share. There'll no longer be bikes on the road. We got new railing, we got new protective screening so people don't throw stuff on the highway. So that takes care of the widening for more cars, makes it safer for peds and bikes. Any questions? Probably a good point to stop. Did anybody have any questions on seismic design or widenings or anything like that? Don't be shy.
You cannot unmute yourselves, but you can type the question either in Q&A tab or in the chat.
Ask lots of questions. I get nervous when people ask questions. Whenever I hire a new engineer, I always tell them, ask lots of questions. I'm shy today. So next up, we're going to talk a little bit about post-tensioning. What's post-tensioning? What's pre-stressed? What are those terms? So typically when we build bridges, we build them out of concrete and we build them out of rebar. And we marry concrete and rebar together because concrete is really strong in compression. If you try to smash it, you have to try really hard to break concrete because it's really good in compression, but it's really bad in tension. So if you have a long piece of concrete, you can snap it pretty easily or just snap it. It doesn't take much, but it's good in compression, but it's bad in tension. Now, steel, on the other hand, is really good in tension. If you take a steel bar and try to stretch it, you're going to have a hard time. So that's why we kind of marry the two together. When we have reinforced concrete, it's both good in compression and tension. So historically, we've taken care of the steel part of that with just standard rebar that's in that left-hand picture. It's just forged or extruded, and we place the rebar in the concrete, and now it's got tensile strength and it's got compressive strength. Well, somebody about 70 years ago figured out that instead of using just standard rebar, if they use a cable, or we like to call it strand, if they use a cable and they tension it, and then they pour the concrete around it, you induce more compressive strength and kind of counteract any tension forces, and it makes it really stronger, and it makes it a much more efficient shape, and our bridges can be longer and they can be thinner. So somebody got really smart and they figured out that instead of just using standard rebar, if we take a cable and we tension it first, our bridges are much better, much stronger. And if you look on the picture to the right there, that's a spool of pre-stressed strand, as we call it, or post-tensioning cable. It comes in big strands like that. If you look, I think on the NEPRIS website, I also had a link to the Post-Tensioning Institute website on there. And that's kind of more technical stuff for engineers, but that's a good website. And if you go into YouTube and just type in post-tensioning, there's tons of videos about installation and how it's designed and the science behind it, and all sorts of videos, technical and non-technical. Lots of good resources there. But this slide kind of illustrates the efficiency of it. So both of these, on the right is the old bridge, which is concrete and regular reinforcement. And on the left is the new bridge with pre-stressed post-tensioning strand in it. Instead, it's going the same distance, but you can see on the left, it's not nearly as deep. There's not nearly as much concrete. So it's much more efficient shape. It uses less materials. It can go farther. It's not as deep. So if you're trying to get tall trucks underneath it, that's an advantage too. And that was one of the advantages here. Based on this bridge where we're widening it, it's actually sloping down. So the trucks were going to hit it. So we needed to come up with a better way to go thinner compared to the old section, or it wouldn't be, we wouldn't have enough clearance under it. So here's kind of a picture of those web walls, those stem walls. So that's what these look like here before the concrete is poured. What we do is they put all the regular rebar in there, and then they put these pipes in here called ducts. And this is where we pour the beam full of concrete, and then we pull the cables through these ducts. And then once the concrete's hard, then we tension those cables, and we compress it. We compress the bridge. So this is kind of before the concrete. You can see all these ducts in here, these pipes. They're getting all those placed and ready to go. So what happens is we'll pour the concrete and then we'll anchor the cables and then we'll tension them, and it kind of picks the bridge up ever so slightly, puts enough tension in it. And then when a truck drives over it, it kind of counteracts that force pushing down on the bridge as the truck goes over. So you've got one thing pushing down, which is the vehicles, and then you've got this pre-stressing strand or post-tensioning that's picking it up, and they kind of counteract each other, and that's where you get that efficiency. Whereas opposed to we just had regular rebar and it'd be like that, and then the trucks would go over it, and you'd have to kind of counteract that. So we kind of start off in a better position. And then here, I'm going to show a little video. These guys are actually starting to pour the bottom of the bridge. So they've got the stem walls formed up or placed with the regular rebar, and just starting to pour the bottom. So this is, they get all the rebar and the duct set, and then they pour the bottom, and then they pour these little walls, and then they come in here and they pour the deck. And I'll show you that deck pouring in a minute. These guys are just starting to place the concrete now. And we can't get the trucks in here, so they've got this pump truck that pumps it in from the crane from about 100 feet away. And then next I was going to show you a video. So this was just in December. They were installing the post-tensioning strand into the duct. So they've right now where they've got this at, they've poured all the concrete work. They've got the ducts. Now they're going to pull this cable through here and get ready to tension it. So this is the cable. There's a guy on one end of the bridge about 300 feet away. He's waiting for the cable to come through, and then this guy's on the one end feeding it. So he cuts, and each one of these ducts has a big bundle of strand cables in it, maybe a dozen. You can see it in the lower right there. Now they're pushing another one through. There's a little machine with just a couple simple wheels that turn and push it through. And then you can see the big bundle of strand there that it's coming off of. Get ready to feed another one. So he puts this little tab on the end of it. And that's just so when he's pushing it through there, it doesn't damage or get hung up on the duct. So a lot of safety and communication that, that guy is in communication with the guy running the machine that's feeding it through, and then they're talking to another guy on the other end of the bridge. So that as soon as it pokes out the other end, he's like, hey, stop. And then they got all the strand pulled in all these ducts. You can see all the strands sticking out, just tons of them. So now they're going to take this jack, this ram, and they're going to put it down there, and they're going to tension these cables up. And there's a sequence to this, kind of like tightening down the lug nuts on a tire. You want to tension this bridge. You want to do it all evenly. You don't want to like over tension it and break it. So they bounce around between the ducts, so this thing slowly lifts, and they're all tensioned evenly.
Quick question, if I may.
Sure.
How safe is this communication method? I'm just watching the video and everything, and the guy is saying, "Okay, hey, stop." So, how effective is that? Or it's a huge what do you call them, excavator or something that they are operating? So, just wondering how.
Yeah, it's definitely dangerous work, and if you haven't been on these teams or these crews a long time, it's definitely dangerous. A lot of it is learning the process, and as an inspector and as an engineer, where it's safe for me to stand. How do I communicate with these guys? They obviously use a lot of hand signals. Construction sites are very noisy. So a lot of times, everything is by hand signals, you're telling people to stop, you're telling the crane to go up, you're telling them to stop. So, they're communicating. They may be on radios, or it may just be very subtle hand signals that they're constantly keeping an eye on each other, watching for those signals. But yeah, you'll watch here in a minute when these guys start to jack this thing up and they start to put pressure to the hydraulic ram. There's not much communication going on there. The one guy does his task and the other guy immediately starts doing his task. But it's post-tensioning and pre-stressing is definitely very dangerous. This ram, it's pumping stuff up at 60,000 pounds per square inch. And if these strands, one of these cuts loose, it could shoot out the other end of the bridge like a missile. So it's definitely. This is a hydraulic ram, and it'll grab that entire bundle of strand in one shot. So he's got little plastic pointy ends on the ends to make it fit into the machine. He's got a little spacer bracket there that spaces them all out. But that ram probably weighs 500 pounds. He's nodding to his guy. Okay, it's good. Hand signals. Just like a sports team, as you're playing with your teammates, you get to learn each other and know each other and learn how to work with each other. Now he's getting it all lined up so it's in perfect angle with the duct. He wants it to be right in line with the duct. He doesn't want it kinked or it'll push where he doesn't want it to. Getting it all seated. See here pretty quick, as soon as he's done, the guy off camera is going to push the button and you'll see that piston start to retract. He's pumping it up already. The piston's retracting. So it's pulling those cables. Pulled them about a couple inches. Yeah, see the inspector joking with him. That he didn't even wait for the guy to get out of the way. He's already pumping it up. So where the engineering comes in, the bridge designer knows exactly how much force he wants on a duct. And then he'll calculate based on the strength of that cable and the size of the cable. And then there's a gauge on that pump that gives him a pressure. And once it reaches a pressure, he knows that we've got the force that we want, that they're tensioned to the amount that we want. One way to back check that is we know the strength of that cable, and depending on how long we stretch it, we can back calc how much force is in that. So we kind of have a way to check ourselves. The gauge will pump it up to a certain PSI, and then we see how long the cable is stretched, and we can back calc what that force is. So then we can kind of check ourselves. So that's what he's doing right there. So he's got a gauge on this, and it tells him he's at 50,000 PSI, and that's what his calculations told. Well, then he can back check, and he's measuring it. Okay, how far did I stretch it? Does that match what my gauge says? And the last thing I wanted to show you was, or the last video was of the bridge deck for. So concrete placement for bridge decks is kind of unique in construction world. We use what's called a bidwell machine. And we use a bidwell machine because we want all the concrete to be dense, and we want all the voids out of there, and we want it really nice and consolidated, but we also need a smooth surface because you're going to be driving your cars on it. It needs to be a smooth surface. So we use it's called a bidwell machine, and it's kind of unique to bridges. And that is what the bidwell machine is. The guys out in front of it, they're the ones placing the concrete and shoveling the concrete. And then the machine comes up and it travels across the bridge on a rail system. And it has augers out in front that kind of knock it down. And then it has these rollers that vibrate it down and make it smooth and kind of knock it off. And then it has a couple pans that kind of make it smooth again. And then there's a couple guys that finish it off and float it with a big bull float. And then it's done. I'll show that again. With this machine, it travels down on a railing system, and it goes back and forth, and then it advances and goes back and forth, and it advances. And there you get your nice, smooth, hard bridge deck that'll hopefully last 75 to 100 years. And then you can see the guy in the gutter, and these guys are concrete finishers. They kind of come through and just make sure there's no holes or rock pockets or any defects. But it's a pretty cool process. My mentor always said that's kind of the coup de grace. It's kind of the make or break. If the bridge deck isn't smooth and right, everybody's going to know about it. The rest of the bridge could be awesome, but if the bridge doesn't drive nice, it's not going to be a good project. And then lastly, I guess, what can go wrong? So lots of stuff can go wrong. So we had an unusual failure on this one. I've never seen it before. So when they're putting that ram against those cables and they're jacking it, like I said, that's like 60,000 pounds of pressure right there. And if the concrete right there at the end isn't good and consolidated and the rebar good, it can blow up. And so that's what happened on one of the ducts they were doing out there. They were tensioning, they were about done, and then they heard this loud crash. They're like, what's that? Well, at the far end of the bridge where it was anchored, there was some voids behind this ram back here in the concrete. and the plate that they were pushing against crushed and snapped and broke. And so they had to, that's what this top corner is. They had to go in there and they had to dig all this concrete out and get all the defect out and the void and reform it and pour it. So you never know what's going to happen. And then the photos are on the right. I'm sure everybody here enjoyed the snow and the ice last week, but we were supposed to go in there and finish some work last week, but we couldn't because it was too cold. So we finished it up this week. Looks like we got a couple questions.
Yeah, so there's a question. So Lauren is asking, how do you know if a bridge needs to be replaced? Is it just about the supports, or there is something else you guys check?
Yeah, so when I'm not building new bridges, I go out and inspect old bridges. We inspect 500 old bridges a year just to make sure they're good. And all bridges that the public drives over, they have to be inspected every 2 years. So I do a lot of that. We look at two things when we're looking at a bridge, whether it needs to be replaced. One is the condition. You know, is the steel in good shape? Is the concrete in good shape? You know, is it holey? Is the timber rotten? So we look at the condition. That's the one thing we look to see if it's replaced or not. And if it gets in bad enough condition, if it's in poor condition or serious condition or things are starting to fail, then we'll replace it. The other criteria that we look to see if a bridge needs to be replaced is it functionally obsolete? And that might mean the bridge is in perfect condition, concrete's in great shape, the steel truss is fine, but it's got some functional problem. Maybe it's too narrow. You know, maybe it only has one lane and it needs 3 lanes because there's just too many cars that go across it, so it's a bottleneck. That's one thing we look for functionality. Maybe it's an old truss and trucks can't fit through it, or it's too narrow and trucks can't fit through it. That's a functional thing. Or maybe it's in good shape, but it's 100 years old, so it was never designed for the big trucks that we use today that are 90,000 pounds. Maybe it doesn't have sidewalks. Maybe it doesn't have shoulders. So we look at all these functional things that are current standards. So we look at it, does it meet current standards? Is it functionally fitting? Some examples of functional issues in the metro area today. You know, we have the I-5 bridges over into Vancouver. That's actually 2 bridges. There's one that was built in the teens, 1910s, and then the one I think that was built in the 50s. The one bridge that was built in the early 1900s, it was actually originally designed to have a railroad on it too, a trolley line between Portland and Vancouver. So it's actually really built stout and strong because it was designed for a train as well as cars. And it doesn't really have any condition issues, but traffic backs up every night, people going home from Vancouver. And why? Because it's only 3 lanes and it doesn't have any shoulders. So it's functionally obsolete because it doesn't have enough lanes because more cars use it than it was designed for. And 2, it doesn't have shoulders. So if a car breaks down, it can't pull off to the side and let people pass. It's stuck there. There's no shoulders. So it's got functional problems. And that's why it needs to be replaced. And bridges are graded on a score from 1 to 100 or from 0 to 100. 100 being a perfect brand new bridge and 0 being a bridge that failed and is on the ground in a pile of rubble. And so bridges get graded based on their condition and functionality. And once a bridge gets a score of less than 50%, it's usually targeted for replacement. And sometimes condition drives that, and sometimes functionality drives that, or a combination of both. There's a whole specialty in just bridge inspection. I think that's everything I had to cover. We're right about 3:48, so pretty good for time. Does anybody else have any questions? Do you want me to revisit any of the slides or photos? Or I've got Google up too. We can we can talk about anything and everything bridges if you like.
Well, I don't know about the kids, but watching your presentation, I have few, if you can answer my questions. In the beginning of the slides, you were showing the shapes of the bridges, the curves and everything. So quickly, a question popped, which is the easiest shape of a bridge to build?
A beam bridge is, well, I would say a beam bridge is typically the cheapest and easiest, cost effective, but arch bridges are, a pretty economical shape. They're a historical shape. I mean, the Romans and probably even before them figured out how to build arches. The thing with arches, though, you have to have a really strong ground. Where the arch lands, this needs to be bedrock. So we don't have a lot of arches here in Oregon because usually our bridges sitting on dirt, but probably beams are the easiest. They're the most basic. Arch bridges are pretty functional if you got the right support for them. Yeah. When you're trying to pick what type of bridge to use, there's a lot of things that go into that. It's like, what are you trying to get over? How much money do you have? Do you care about aesthetics? The last 30 years, most people don't really care about what a bridge looks like. They're just trying to get across the river as cheap as possible. So, the last 30 years, we were doing a lot of, beam bridges. And also nowadays, most of the bridge cost is in labor. It's in paying people to build the bridge. It's not necessarily materials. Where during the Great Depression 100 years ago, labor was cheap.
Yeah.
And materials were expensive. So they built a lot more beautiful bridges back then because labor was cheap. You could afford to pay masons and stonemasons and all these great craftsmen to do work because you were paying them nothing. Nowadays, that's where all the cost is. So they're more simplified.
Nowadays, they just build the Golden Gate Bridge and they are happy.
Yeah. I mean, the Golden Gate nowadays would take you 100 times more money and 10 times as long as it did back then. So, a lot of these bridges that they built 100 years ago, they would have had a crew of 100 guys out there working on it, where today we'll have a crew of 10.
Yeah.
They would have had an army.
But with all the type of, the new technology and the things like the excavator and all the latest things that you have, won't it take lesser time than it used to?
Not necessarily. I mean, they built bridges really fast back then. Well, one thing that they didn't have to concern themselves with back then was safety and environmental laws.
Yeah.
So when we're working in the water, usually if it's a salmon in the stream, we're only allowed to do that during a couple months during the summertime. We have safety restrictions. So we have a lot more constraints put on us. We just can't attack it and do whatever we want. We have to be mindful of the environment. We have to be mindful of traffic and the community. We can't be out driving piling at 1 a.m, keeping the neighbors awake. So, that probably has a lot to do with it.
Yeah. Students, any more questions? Or I'm the one, I can go on and on. It was such an interesting presentation. I have so many questions.
I'm going to put my email in the chat. If anybody has any questions afterwards or wants to come in and do a job shadow, don't hesitate to reach out to me. Always available.
But before you go, I have one more question that's bothering me, if I'm not taking too much of your time.
Well,
so we know US. I have traveled to Australia and seen, and there are a lot of bridges and beautiful bridges. So my question is, what, according to you, is which country has the most beautiful bridges?
I'm not much of a world traveler like you. You probably got much more frequent flyer miles than me around the globe. I'm kind of a history sucker, a buff, so and I love a good stone arch. So I mean, the Mediterranean's got a lot of great stone bridges, and I really enjoy that. But I mean, Asia right now I think is on the cutting edge. I mean,
Yeah.
they're doing bridges bigger and bolder than anyone as far as cable stay and suspension bridges. Asia's got a lot of great bridges. America's got a lot of great bridges. Oregon's got a lot of great bridges. The Oregon coast with Condi McCullough's bridges that he designed. I mean, there's amazing structures. We've got a lot of, I think we've got 40 covered bridges in the state that are, a lot of different covered bridges that are real beautiful. I always enjoy looking at those. So, yeah, each country definitely has their unique designs, and they build bridges out of the tools that they have at hand. So.
Yeah. Well, okay, fascinating. You have just opened so much new things about constructions and bridges.
Yeah, you're welcome. Well, thanks for coming, everybody. I appreciate it. I hope you got something out of it. And yeah, don't hesitate to reach out if you have any questions or comments.
Okay, with that, thank you so much, Jason. Thank you for taking out time and doing this wonderful presentation. I, of course, learned a lot. It was fascinating. And thank you, students, for joining. Hope you all have a good rest of the evening.
Yeah, thank you all for coming. I hope you're all back in school here in a few months to come. So have a good rest of your week.
Okay, thank you all.